Greetings to you all. This is Naziwali Metrin, together with my colleague Marvin Benjamin Chivumbi. Our presentation this evening or afternoon is going to be about the balancing robot, a two-wheel balancing robot. In accordance to a course unit we are doing called Mechatronics Design, and the work is mainly going to be about modular refinement and hardware validation. To start with, the balancing robot was modeled, and the Simulink model of the balancing robot is presented in this presentation together with a controller added to the system later on. And then we test the system using different types of forces input, and also we test the system with no external force, and finally we give system dimensions and specifications based on the actual system existing. To start with, the main objective here is sensor actuator design and selection, further modular modeling and parameter tuning, and finally simulation and analysis. And gradient function is here as shown, and after deriving and resolving the force to different angles and the velocity, we come up with two equations. One is shown here and the second one is shown here, and finally they are linearized using Taylor series expansion, and these are the final two equations we have that represent the system model. From that, we are able to come up with a Simulink model of the balancing robot as shown here, as shown below. Right here is that first model that you're seeing in our document that shows able to plot our values from the different theta and y, and this is the graph we end up with. To go on, the characteristics of theta and y reveal that the system is unstable and hence a need for a controller. So we go ahead to look into different controllers that we could implement for the system, and the first we look at is a PID controller. A PID controller is mainly proportional, integral, and derivative controller, and it's also known as a three-term controller, and all those three are varied in different ways to be able to give us different values. So we shall look into our system, and back here in the Matlab file, for the first case, for the first scenario, which is this, where we have a PID put onto a system. Sorry, we have a PID that is put onto a system that has a force impulse as the input, and that's our first case here. We have an external force as the impulse force that is being put in, and mainly what an impulse force is that you apply it for a certain period of time and you're able to see the result for that particular period of time. Then the force is returned again after that particular period of time. So for an impulse force with an amplitude of 11 with a period of 3 seconds and a pulse width of 0.01 with 0 phase delay applied to the system, this is the particular result we have here. This is a particular result we have where y is our output displacement of the robot, and then our blue graph is the theta as shown from the legend here. And mainly for an impulse force with an amplitude of that's what we are able to observe. So then we go ahead to try and multiply that amplitude by 5 with the same period and the same phase delay and pulse width, and this is what we get. So when you observe clearly, the difference is in the amplitude of theta and y. When you look here and you try to look here, you realize there's a difference in the two for both force impulses. And from both graphs, it's shown that the linear displacement y of the cat increases and falls back to the initial position, then gradually continues increasing in that direction, and the amplitude of the tilt angle increases and falls back to 0 with within about 1 second as the system requirement. This shows that the system is stable in balancing when we apply the PID. It is in the Matlab file. It's just a matter of connecting this here, and then we have a unit step that is applied to the system. And on running our file, this is the output we are able to get. And from the above, we are able to see that when a unit step force is input, it's similar to a constant force applied to the system, and the robot moves in the opposite direction to balance and continues in that direction since the force is not withdrawn. However, the tilt angle will not return to zero because remember we are applying a constant force. So with that constant force, the system will remain at that particular angle it has been displaced to, and it will not return to zero. And also, the displacement will only keep increasing in the opposite direction. And that is what we see from this graph here, that the angle will move from zero and grow, but it will grow to a certain value and remain constant for the whole time, and then the y will just keep increasing. Then for a system with no external force, which could be this case here on the other side, if this is removed, we could have a system assuming that the initial tilt angle of the pendulum is 20 degrees for this particular simulation. Without an external force, the system stabilizes in the required time, 1 second. However, the tilt angle drops and the robot stabilizes at 0. The linear displacement drops and stays constant since no external force is applied. So when you look at this graph, we've said we are starting with our tilt angle at 20, and converting 20 to rads per second is about 0.49, which could be this blue graph you're seeing here. So initially the angle starts from 0.349, and our balance point is 0 for this particular robot. So for the robot to balance, it will have achieved 0, and that's what we see here, that the robot angle drops and then later on goes to 0. And then the displacement also drops and keeps at a certain constant value because we do not have an external force applied, which is already what we expect to get as explained above. The other kind of controller that we could have looked at to control our system is a state feedback controller, which is particularly applied as follows, and the schematic of this type of control is shown, where K is the matrix of gains. On this other end, in the Matlab file, to illustrate that, could give a quick view at this particular system here. And in reference to that, we can see that we have a matrix here B, we have a matrix here C, and here is the gain, the particular gain for the controller. And when we click here, we should be able to see the different constants. This is a constant that is read from the Matlab file. From this particular Matlab file here. So this value here of the different terms we have from the matrices A, B, and then Q, which is here, and R, which is here, we are able to model a state space controller to the system. Yes, as follows. So this is how we're able to implement the state space controller, following the different parameters here, the linear quadratic regulator. We're able to model this in Matlab, and we're able to get the following results. So the first result is this. The blue graph represents the displacement y of t, while the red graph represents theta. So angular displacement of the pendulum here is in radians, and the design controller stabilizes the robot in 6 seconds, yet we desire stability in 1 second. This other graph represents the state vector matrix of the system, which includes y dot, theta, and theta dot. These are mainly our state vector matrix, which is viewed here at this particular scope. Then this upper one of y of t and theta of t is viewed at this particular scope. So those are our two different values. And then for the system and the design specification based on the real component system, we have a length of 0.2 meters, we have a width of 0.4 meters, we have a radius of the wheel as 0.04 meters, we have the mass of the pendulum as and the mass of the robot as 1.1 altogether, and then we have a maximum tilt angle 5 degrees, and we desire that the settling time is less than 5 seconds. Moving on to sensor selection, a suitable sensor chosen for the use in the system is MPU 6050 IMU sensor, and the datasheet is attached to provide the different sensor specifications. Modeling of the sensor based on the manual and datasheet. Actually, Matlab has an IMU block that we could use to model the different parameters of our sensor. However, this block here, the values that are supposed to be input into this block are constant, yet we would desire to pick our values from the system as variables to be able to be read by the sensor. So that makes it a little bit hard for us to use this block. However, the block is explained below and illustrated, and if we would desire to use this block for the actual values of our parameters, we've actually tried to input the different values from the datasheet. And here it is the values of accelerometer, gyroscope, and they are set to match the ones of the sensor datasheet. However, the issue is still that the components that are input here for linear acceleration are supposed to be constant values, yet we have varying values from our system. So we then resorted to using the MPU 6050 IMU sensor block, which is as shown below, this particular one. And it reads data from the sensor that is connected to the hardware, and it measures acceleration, angular rate, and temperature along axis of the sensor. So it has block outputs, and those are acceleration, angular rate, and temperature. However, for this particular work, we focused on the acceleration and the angular rate, as you can see, as it's noted below. And those outputs are as a 3x(n) double precision array. And hence that means we need to change them to values that can easily be read by adding a filter at the end here. And that filter chosen was a complementary filter. Complementary filter consists of both a low pass filter and a high pass filter, as shown. On this other end, it's this. I can just comment it out. It's this. So we have a complementary filter that consists of both a high pass and low pass filter. So on simulation, we desire that this particular block helps us pick values from the actual IMU sensor that we've put on the system, and those values are fed into the complementary filter, which is later giving us the angular velocity. And this particular block is to help us change the values back to our values that we were originally reading, and then display them on the scope. That's it for the first bit of the balancing robot. Thank you so much.